Hello, and welcome to Astronomy 100. In this segment, we're going to begin a new section, and in this section, we're going to talk about the seasons. And the topic of the seasons is a very important one in astronomy for a couple of reasons. First of all, the seasons has a description to the explanation as to why we have seasons that's astronomy related. Essentially, the reason why we have seasons has to do with how the Earth is moving in its orbit and how the Earth is spinning on its axis relative to the Sun. So there's definitely an astronomical component to the topic of the seasons. But the second reason why we're going to make sure that this is an important topic that we include is because many people think that they understand why we experience seasons, but then when we ask them to give us their explanation, what we find is that their reason that they give for the seasons, their explanation, turns out to be incorrect. And the reason for that is because there is an idea that seems plausible, that sounds very good, but that just turns out to be incorrect. So what we're going to do in this section is we're going to talk about the reason why the Earth experiences seasons, and we're also going to take an opportunity to hopefully get rid of the idea that is commonly understood that turns out to be wrong, and replace it with an idea that is correct. Now, the topic of the seasons is something that many people take for granted. We often are familiar with the normal changes that occur in our weather, and depending upon where you live in the country, these changes that occur over the course of a year may be very trivial. For instance, I live in San Diego, and in San Diego, the seasonal changes just don't seem to be very much. The temperature outside during a cool autumn day is really not a whole lot different than it is when it's a cold winter day, or the hottest summer day is not really a whole lot different than maybe an average winter day. So we just don't have these dramatic seasonal changes. But there are places around the world that definitely have very dramatic changes to their conditions of the environment outside related to the seasons. And these changes can be quite severe to the point where they can be dangerous if you're not familiar with how these things change and progress. The other and the final reason is that historically seasons were an incredibly important idea to the ancient people of the Earth. The reason is that they had to pay careful attention to what season it was, so that they knew when to put the seeds in the ground, and they knew how long it was going to take to have those plants grow, and they knew when to go outside to harvest those crops. And if you somehow messed that up, if you didn't get the seeds in the ground at the appropriate time, or if you didn't harvest the crops at the appropriate time, it would mean that you could perhaps starve to death. So ancient cultures of the Earth were very tuned into the seasonal patterns and the changes because it really meant something that was related to their survival. So let's start with our first picture here. The first picture that I want to start with is one of my favorites, and what it is this is a series of 4 photographs that were taken in the backyard of somebody, and this man who went outside, what he did was he made sure to take the exact same picture of the exact same tree from the exact same location at the beginning of each season. So you can see here in summertime, his tree in his backyard, and I suppose the bird bath there. And then the first day of autumn or fall, you can see the tree has changed quite dramatically. And then of course the first day of winter, we have the snow on the ground, the tree has lost its leaves. And then of course we have the first day of spring, where you can see the blossoms occurring on the tree again. So very dramatic seasonal changes occurring from this person's location. This is clearly something that I don't see in my backyard here in San Diego. So what we're going to do is talk about these seasonal changes. But before we can do that, we have to start off with how the Earth orbits around the Sun. And the revolution of the Earth orbiting around the Sun is a period of time that we call the tropical year. And if we measure how long it takes for the Earth to make one orbit around the Sun, it takes 365.2422 days. Now, it's very obvious that the number of days that it takes the Earth to orbit the Sun is not a perfect integral number of days. In other words, it's not an exact integer, 365 or 366. It's 365 and then some extra, 0.2422. Now this extra little bit is fine. It's just because the universe is the way that it is, and it's not going to be a perfect number of days when the Earth orbits around the Sun. But the fact that it's not exactly 365 days or exactly 366 days actually poses a bit of a problem that has to be dealt with. Early on in human history, we just weren't sophisticated enough to know that it was 365.2422 days. The early calendars that we were using were just primitive, they were not accurate, and many of the early calendars didn't even have the ability to tell us that it was 365 days. Some of the early calendars showed that it was about 350 days. Some of the calendars had it as many as 370 days. But when calendaring became more sophisticated, when we had the ability to determine the passage of time in a very accurate way, it became clear that it was 365 plus a little bit extra. This 0.2422 had to be dealt with. The first reaction is to just kind of ignore it, to just simply pretend that the year is 365 days long. But the problem is that when you force your calendar to be 365 days, when in reality it's 365 plus a little bit extra, it means that there's an inaccuracy that will start to accumulate. Now you'll notice that 0.2422 is very close to 0.25, and 0.25 is 1/4 of a day. And if we translate that into hours, that's 6 hours. So what we're really talking about is how the period of time that it takes the Earth to orbit around the Sun is 365 plus a quarter days. Pretty close. And so this quarter day, this 6 hours, sounds trivial, but notice what happens. If we force the calendar to be 365 days and we ignore this extra little bit, after 4 years of ignoring it, after forcing the calendar to be 365 days for 4 consecutive years, you have now ignored a full day. So your calendar is now off by 1 day. If you do this for year after year after year, generation after generation, eventually your calendar will tell you that it's summertime, but you'll go outside and it'll have the conditions of autumn. Or if you wait long enough, you'll have the conditions of winter. So you want your calendar to match the actual season that you experience outside. So eventually, we became aware of this fact, and there was the desire to fix this, the need to make sure that our calendar is accurate. Now, the very first attempt to fix this is one that involves a term you've probably heard before. It's the term leap year. And the idea actually goes back to none other than Julius Caesar. Now, in 45 BC, Julius Caesar was somebody who commanded his mathematicians, the people who worked for him, he commanded them to fix this, to come up with a way to fix this problem. And so what they came up with is a system that would force the calendar to always be accurate, and it's what we call leap year. You're probably familiar with the idea, but let's go through it a little bit. Leap year is the idea that we will just simply assume that the calendar has 365 days. In other words, we're going to ignore the 0.2422. We're going to do that for 3 years. So the first year it's 365 days, the second year it's 365 days, the third year it's 365 days. But on the 4th year, you have now accumulated a full day of error. So on the 4th year, you add a day to the calendar. So every 4 years, we have a calendar that has 366 days. And currently, we end up adding the extra day in February. So if it is leap year, February has a February 29th. So this system means that we can correct the calendar to more closely match what the Earth is actually doing when it comes to its orbit around the Sun. But here's the problem. 0.2422 is not 0.25. And so if we assume that it's the same, if you look at the screen here, what we find is that after 128 years of using the leap year system, our calendar will be wrong by a day. So 128 years of using leap year, the calendar is now off by 1 day. That sounds trivial. 128 years is a long period of time. But in reality, that starts to add up quite substantially as the centuries go by. So there was the need for another fix. And this occurred in 1582 when Pope Gregory XIII comes along and he commands his mathematicians to fix this problem. Because from 45 BC to 1582, there had been the accumulation of several days. The calendar was off by quite a bit. And so what was adjusted was a modification to the original leap year system. And so what Pope Gregory's mathematicians came up with is just a tweak to the way that the leap year system was originally designed. And so I'm going to show you how this works. It's a little complicated, but follow along and see if you can understand this process. The way that it works is if the year in question is a century year, meaning if it's the year 1600, the year 1700, 18, 19, or 2000, on the year that is a century year, you do an additional test. Remember, every year that is a century year is normally a leap year because it's always the fourth year. But if you take this additional test, what you do is you take the year in question and you divide it by 400. If the year divides by 400 and has nothing left over, no remainder, such as in this case it does, then what you do is you go ahead and have your leap year as normal. So the year 1600 was a leap year. But the year 1700 was not a leap year because 1700 divided by 400 is 4.25. There's a little bit left over. So on the years that don't evenly divide, you skip the leap year. So the year 1700 should have been a leap year, but because of this new system, it was skipped, just that year. So 1696 was a leap year, 1700 was not a leap year, 1704 was again a leap year. So 1800 does not divide equally without any leftover, so you skip it. 1900, you skip it, and then on the year 2000, it does again divide without any remainder, and you have a normal leap year. So this tiny little tweak, this tiny little fix to the original leap year system provides a way for us to now figure out how to make the calendar be just a little bit more accurate and match what we actually see the sun doing. And so, but this is of course not perfect either, because this new system of doing it that's been in place since the time of Pope Gregory, after 3,236 years of using this system, the calendar will be off again by one full day. But you'll notice that you have to have more than 3,000 years go by before you accumulate the 1 day's worth of error. Whereas the previous system, only 128 years go by and you get the error. So this calendaring system that we currently use today is called the Gregorian calendar. So that's what we are currently using, is the Gregorian calendar named after Gregory. The original calendar was called the Julian calendar. So from 45 BC to roughly the end of the 16th century, we had a Julian calendar, and now we have what's called a modified Julian calendar, or a Gregorian calendar, which keeps the leap year system, but with this additional modification. And this is currently how we force the calendar to match what we have with what the Earth is doing in its orbit around the sun. And this will always maintain the seasonal changes to match what the calendar is saying. So if your calendar says that it's summer, of course the season will actually be summer outside, because we don't have any drift or any change between what the calendar tells us and what the seasonal changes actually are. Now what we're going to do is we're going to talk about how the orbit of the Earth around the sun is what ultimately gives us the conditions that we call the seasons, and how the seasonal changes are related to that. But that's a big topic, and we're running a little short of time, and we're going to begin with that next time. I hope you'll join me.